Hello everyone, my name is Sofia Nicolaidou and I am a data scientist at KYAMOS Ltd. Today I will introduce the REALISATION-INVERTERS-PV project, which focuses on the real-life simulation for monitoring and controlling inverters of small PV parks. This project is funded by the European Union through the NextGenerationEU instrument and by the Republic of Cyprus through the Research and Innovation Foundation. In this presentation, I will describe the problem overview, the project's objectives, our methodology, indicative results, and the conclusion, which includes the key outcomes of the project. Let's dive into the project's overview. In Cyprus, where our study is taking place, the inverters of small PV parks are not connected to the SCADA system, and so they are not continuously controllable. That means that when grid instability occurs, these inverters either continue injecting power to the grid or get fully disconnected, and this can worsen instability or even threaten equipment safety. Thus, there is a need for a low-cost and fully autonomous control system to monitor grid conditions and decide when and how much to curtail PV output through the inverters. So the goal is to detect early signs of instability and make instant power adjustments. To achieve this, we set up our own hardware so that we can process all the data efficiently and have continuous control over the inverters. The idea is to run our software on high-performance GPU clusters to support data-intensive processing tasks. Secondly, we needed to consider the electrical grid surrounding the PV parks. And since it is difficult to obtain real data, we emulated realistic grids, setting each component's parameters and specifications. We also utilize AI algorithms to predict when the grid is unstable and how much to curtail power through the inverter. Moreover, we incorporated all these technologies into the KYAMOS graphical user interface for real-time monitoring. Lastly, we deployed a secure data transmission system between the inverters, the Raspberry Pi, and the server, achieving seamless communication. For our hardware, we have built two GPU servers supporting rapid parallel processing and heavy AI training. We have also built a Raspberry Pi prototype for constant data acquisition and inverter control. Note that we made our Raspberry Pi entirely self-sustaining by connecting it to a mini solar panel and a battery, as illustrated in the figure here. Regarding our graphical user interface, we created a user-friendly interface where users can choose to have manual or automated control of inverters according to their needs. We incorporated system alerts for grid instability, inverter on and off buttons, and data visualization tools. Users can also create the grid relevant to their PV park. For this, we included a list of distribution network components like wires, buses, loads, and transformers, and we enabled drag and drop capability to make the process easier. Here you can see the architecture of our communication system. In our project, we use the Fronius SIMO inverter that communicates with the Raspberry Pi using the Modbus TCP/IP protocol. In this way, we collect the inverter's data and we perform pre-processing tasks such as scaling and error handling. Also, the Raspberry Pi communicates with the server efficiently and securely, passing the pre-processed data to our server. From there, users can visualize the results using the graphical user interface. On the other hand, users can introduce the commands from the graphical user interface, and these commands will go from the server side to the Raspberry Pi, which will control the inverter. Moving on to the AI, the system uses reinforcement learning for intelligent inverter control. The AI is designed to predict voltage deviations, execute power curtailment actions, and trigger inverter disconnection only when necessary, with the ultimate goal of predicting how much PV power should be supplied to the grid. We applied advantage actor critic methods, specifically A2C and A3C, to efficiently learn optimal control policies under dynamic grid conditions. Advantage actor critic methods can be either synchronous or asynchronous. The A2C model is the synchronous model where all workers wait each other to update the global network using the same optimizer. On the other hand, the A3C model is the asynchronous one where each worker runs its own environment and updates the global network at its own time asynchronously. We also consider a deterministic model that uses binary search to find the local optimum of the power curtailment, prioritizing voltage stability and minimizing unnecessary curtailment. This is called the teacher and it is used as a baseline. This slide presents the global neural network model that is used to train the workers of both A2C and A3C. This network consists of 10 input features, 2 hidden layers, and the actor critic outputs. The widely known ReLU activation function was used to introduce nonlinearity, enabling the model to understand complex patterns. The three output values are alpha and beta of the beta distribution and the value estimate V of the critic. The actor defines two parameters, one that controls if the policy prefers high PV output and one that controls if it prefers power curtailment. So, the role of the actor is to decide how much PV power to curtail, while the critic evaluates how good this decision was based on a reward function. In the A3C model, for each rollout, each worker interacts with its own environment independently, running grid simulations. Then, the reward function evaluates actions, penalizing unnecessary curtailment and voltage violations. Note that the voltage violations are penalized much more than the unnecessary curtailment, since our priority is to have a stable grid. Additionally, the worker computes the temporal difference error and the generalized advantage estimation locally. Then it computes the policy loss, the value loss, and an entropy bonus, which together form the worker's total loss. Each worker stores the state, action, reward, the value estimate, and the log probability of the beta distribution. Backpropagation is used to compute the gradient of the total loss, and then the Adam optimizer uses that gradient to update the weights of the global network asynchronously. Workers reload the updated weights to continue learning from the most recent shared policy. After many rollouts, the AI learns to improve its decisions, minimizing the total loss. For the A2C model, the training involved 4 distinct environments, about 266 simulation days, 5-minute time steps, and 600 updates. Indicative results are shown in the first graph, where the blue line represents the simulated PV power output, and the green line is the power that should be dispatched based on our A2C model. The orange line is the dispatch power predicted by the teacher, which is not operationally ideal and finds the local optima. We can see that our model correctly allows for small violations, maintaining a stable operation. For the A3C model, the training involved about 16 parallel environments and 992 simulated weeks. According to the user's needs, we can make our model stricter, learning safer decisions while also retaining smoothness. Indicative results of this case can be seen on the second graph, where the green line representing the A3C's dispatch power is closer to the teacher's optimal decisions.
Here you can see a demonstration of our graphical user interface. Users can add their PV park and connect or disconnect their inverters using these buttons. They can also see the live frequency of their system with alerts, and they can plot inverters data in this table and produce these graphs of power or frequency. They can also create their own grid and adjust components parameters as they wish.
Summing up, we managed to combine many disciplines together, from back-end to front-end development, creating an autonomous system for monitoring inverters. This prototype has a strong operational impact, reducing the need for full inverter disconnections and offering the users real-time monitoring and control over their PV parks. Results suggest that this system is promising, and there is still ongoing work towards its improvement. For future work, we seek to take our product from Technology Readiness Level 6 to TRL 8 or 9. That concludes my presentation. Thank you all for your attention. If you have any questions, please feel free to write them in the comment section below, or you can always reach out to us using the contact details that are included in this slide. Summing up.